Long before the first dinosaurs shook the earth, our planet was ruled by creatures that crawled, slithered, and hunted through steaming swamps. Amphibians the size of crocodiles, armed with fangs, armor, and sails rising from their backs. These were not the gentle frogs we know today, but giants that dominated rivers and forests in a time when land and water were still learning to share life. From boomerang-headed gliders to bear-trap jawed killers, this was the forgotten empire that came before the dinosaurs, a world where amphibians were the apex predators, and every ripple on the water might have meant your last breath. Prionosuchus, Permian, Brazil's gharial-like titan. A long-legged animal that was longer than most crocodiles slid under rafts of fern and horsetail in the swampy riverlands of what is now northeastern Brazil. The Prionosuchus plumeri fossil from the early Permian Pedra de Fogo formation of the Parnaíba Basin looked a lot like a modern gharial. It had a long, narrow head full of needle-like teeth, eyes set high for watching the surface, and a deep, flattened tail for quick bursts. Broken skulls and skeletons show that the animal was about 6 to 8 meters long, making it one of the biggest frogs ever discovered. In those rivers, it was the last shade fish and small tetrapods saw. Its skull tells the story of an ambush fish-eater tuned to still water. The snout is elongated and lightweight, with thin bony struts supporting interdigitating conical teeth that interlock like zipper teeth when the jaws close. Behind the outer tooth row, the palate bears paired palatal fangs, larger posts that help pin slippery prey. This double-rowed grip meant a thrashing lungfish or palaeonicid fish couldn't wriggle free once caught. The roof of the skull is perforated by grooves of the lateral line system, a pressure-sensing network inherited from fish. Prionosuchus could feel ripples of movement through the water even when visibility dropped to murk. In contrast to later Permian temnospondyls that were short and had toad-like heads, Prionosuchus was an archegosaurid, which means it had a long nose, was sleek, and was very watery. The ribs and vertebrae show that the body was built more for controlling balance than for carrying weight on land. The legs were probably simple paddles that tucked against the body while swimming. The tall, compressed laterally tail pushed the animal forward and could flick side to side for a quick rush. The body language is like a crocodile's, but on an amphibian, it stays still along the bank, glides slowly, and then strikes with an S-curve. Geologically, the Pedra de Fogo preserves a mosaic of lakes, floodplains, and fire-scarred wetlands. The formation's name refers to abundant chert and ancient wildfires. Charcoal layers, evaporates, and fish beds point to seasonal drought and refilling cycles. That rhythm would have concentrated fish into shrinking channels at the end of dry seasons, perfect for an ambush specialist with low energy costs and high strike performance. Tooth microear studies on allied Archegosaurids show polished tips and minimal chipping, consistent with soft-bodied prey rather than shell crushing. Prionosuchus likely patrolled eddies near submerged logs and undercut banks, snapping up fish, small amphibians, and juvenile reptiliomorphs drifting within range. The lateral line and eyes and nostrils that were put on the back allowed for periscope hunts, where most of the body was hidden. It seems like the palate had internal schwannae, internal nostrils, and a stronger skull table, so it could breathe at the surface without taking its head out of its shell. Archegosaurid's ears have a mix of features for conducting sound underwater and above ground. Prionosuchus probably relied more on vibrations than on direction hearing underwater, and on land it was probably slow and short-ranged, only moving from pool to pool when floods made safe pathways available. Size estimates for Prionosuchus have sparked debate because the fossils are incomplete. Early length reconstructions scaled from huge skull fragments produced sensational numbers over 9 meters. Later comparisons to better-known Archegosaurids, such as Archegosaurus deceni from Germany, trimmed that figure, with 6 to 8 meters now the cautious bracket used by many researchers. Even at the low end, it outclasses most amphibians by a wide margin. The combination of a gracile snout and very long body sometimes leads to mistaken identity with crocodile relatives in the field. Closer inspection, labyrinthodont tooth bases, palatal fangs, and the pattern of skull sculpturing anchors it firmly among temnospondyle amphibians, not reptiles. Growth and lifestyle hints come from bone histology in related forms. Archegosaurids show fibrolamellar bone indicating relatively rapid juvenile growth, then a slowdown as adults settled into energy-efficient sit-and-wait strategies. Lines of arrested growth mark seasonal stress, likely the dry-down intervals in those Permian wetlands. The dermal skull bones bear pit and ridge ornamentation that, in modern crocodilians, helps with cutaneous blood flow and heat exchange. In Prionosuchus, similar texturing may have aided thermal buffering during basking between hunting bouts. Mastodonsaurus, Middle Triassic Europe's door-wide skull trap. In Europe, in the Middle Triassic, there was a flat shadow just below the top film in the lakes and floodplains. Only 2 eye bumps and 2 holes in the nose broke the surface. Mastodonsaurus giganteus was that shade. It was a stereospondyle temnospondyle with a head that was long enough to span a doorway. Its head was up to 1.2–1.5 metres long, and its body was up to 5 to 6 metres long. It turned the edges of quiet lakes into places where fish, small snakes, and other animals could hide and be gone in an instant. The skull is the key to everything. Broad and pancake flat, it formed a living bear trap. The top surface shows heavy pit and ridge ornament and a map of lateral line canals, letting Mastodonsaurus read ripples the way a bat reads echoes. The orbits sit high and far back, so the animal could park the head at the surface with almost no silhouette. At the tip of the snout, the external nares sit forward, useful for periscope breathing, while the rest of the skull stays hidden in weed beds or against a mud bank. The lower jaw carried a pair of oversized tusks that projected upward when the mouth closed. Rather than leaving the lips parted, the skull roof has deep tusk pits, sockets that received those daggers so the mouth could seal tight. Behind the marginal tooth row, the palate bristles with palatal fangs, stout posts that meet the lower teeth like interlocking nails. A thrashing lungfish or ganoid fish, once inside, couldn't squirm free. The more it fought, the deeper those palatal posts pinned it. Tooth microwear on related stereospondyls shows polished tips rather than heavy chipping, a signature of soft-bodied slippery prey rather than shell crackers. How did a head this wide move water without warning prey? By barely moving at all. Mastodonsaurus hunted as a sit-and-spring ambusher. The huge sheet-like adductor muscles attaching along the back of the skull and onto the lower jaw acted like springs, slow loading, explosive closure. When the strike came, the flat skull slid forward beneath the surface film, the deep lower jaw rotated up, and the palatal fangs scissored in. In shallow margins choked with horsetail and club moss, the strike path was a straight lunge. In open pools, a quick up-angle snap from below likely produced a brief suction pulse to help draw prey in. Inside the ear region, stereospondyls show a mix of primitive features that suggest poor airborne hearing but good sensitivity to low-frequency vibration transmitted through the skull and water. In life, Mastodonsaurus probably listened with its entire head. Lateral line grooves mapping pressure, the skull table relaying tremors from fin flicks and tail beats nearby. The otic notch, a recess at the rear skull, may have housed soft tissues aiding pressure relief during rapid jaw closure, a useful buffer when slamming shut a mouth the size of a suitcase. The rest of the body was about stability and thrust. The vertebrae are stereospondyle discs, intercentra, that build a stiff front half and a more flexible rear. Limbs were stout but sprawling, better for push-ups and short belly shuffles than for long hikes. Mastodonsaurus was overwhelmingly aquatic. Propulsion came mainly from a deep, laterally compressed tail that could scull the animal into position with minimal wake. Dermal scales are rare to absent. The skin was likely smooth and glandular. crocodile quiet in the water. Why the door-wide skull? Control and regulate the flow of water. A big flat head spreads the force of the strike across the food, stops the surface from bobbing up and down, and makes the pressure drop quickly at the mouthhole, which helps with suction. The tusk pit system lets the animal close its lips without losing the knife edge. This means that it could stay completely shut between attacks, keeping its moisture and remaining stealthy in hot, dry places. Metoposaurus. Late Triassic drought pool giant. Think of a river that has stopped moving in the late Triassic, a chain of shrinking, dirty pools with broken clay and downed reeds around the edge make up the channel now. There are a lot of fish in the last few spots of water. Lungfish wiggle into the mud and turtles nose around in the shallows. Dozens or even hundreds of broad-headed frogs are lying still on the bottom, stacked like paving stones. The famous death lagoons of Poland, Germany and Morocco are made up of large bone beds that belong to Metoposaurus. They tell the story of a giant that won in floods and lost in droughts. Metoposaurus was a metaposaurid stereospondyle, a temnospondyle lineage built around a huge flat skull and a body designed to hug the substrate. Adult stretch 2-3 meters long, with a skull like a rounded shovel, eyes set high, and a short trunk ending in a deep, laterally compressed tail. The limbs were relatively small and sprawled. On land they could push and shuffle, but in water the tail did the work, sculling the animal forward in low, quiet strokes. Skin impressions and bone texture suggest a smooth, glandular hide, no armour to clatter or scrape, perfect for silent ambush in still water. The margin of the skull is lined with close-set, conical teeth, ideal for gripping slick prey. Just inside, the palate bristles with palatal fangs, stout posts that oppose the lower dentition, so anything that slides inward gets pinned. The result is a living fish trap. Lunge, gulp, pin, swallow. Tooth micro-wear on Metoposaurids shows polished tips and little chipping, a signature of soft-bodied prey like ganoid fishes and juvenile tetrapods, not shell crushers. The skull roof is etched with pits and grooves, the map of a lateral line system that sensed pressure changes. Metoposaurus could feel a fin flick in murky water without seeing it. At the Krasijo locality in Poland and similar sites in Germany and North Africa, bone beds hold piles of skeletons that are all from the same species of Metoposaurus. These are the most important fossils found so far. The study of taphonomy, or how bodies are organised and buried, shows a sad cycle. When there was a yearly drought, the animals stayed in ponds that were shrinking, and deaths rose due to overcrowding, overheating, and lack of oxygen. Then quick storms filled the basin with sediment, burying the bodies all at once. Many bodies are articulated or only slightly disturbed, which suggests that they were buried quickly rather than being dug up for a long time. Young fish gather around the edges of the pool, while big adults hang out in the deeper middle areas. This suggests that fish of different sizes use different areas of the pool in different ways. The body plan explains both their success and their traps. The vertebral column is built from intercentra, disc-like elements common to stereospondylus, producing a stiff forebody for stabilizing the big skull and a more flexible tailstock for power. The shoulder girdle is broad and low, great for push-ups and orienting the head at the right angle during a strike. Hands and feet are paddle-like with stout digits for soft substrates. On land, trackways suggest short, sprawling shuffles between pools after rains. In the dry season, many likely estivated hunkering down in the mud until oxygen crashed or the mud hardened beyond endurance. Stomach area associations include ganoid scales, small amphibian bones, and occasional reptile fragments, likely opportunistic takings along muddy margins. Bite marks on co-occurring bones show U-shaped gouges that match metoposaurid tooth spacing. Some prey survived, as evidenced by healed furrows. Competition varied by basin. In some deposits, Metoposaurus shared water with smaller temnospondyls, capitosaucrids, that worked the shallows and phytosaur precursors that patrolled channels. Niche separation kept the giant flatheads focused on still pools and slow eddies where their ambush style shined. Cyclotosaurus, egg-seek, late Triassic pan-continental bruiser. During the late Triassic of Pangaea, a heavier frog with a deeper head roamed the rivers from Central Europe to India's Rift Valley lakes. This stereospondal superpredator took the flat bear trap head of older temnospondyls and made it stronger so it could crush prey. Metoposaurus and its relatives were good at suction-assisted gulping. Cyclotosaurus, on the other hand, added bone and muscle to the same plan to make it a grip and crush machine, perfect for fish with thick scales, lungfish with armour-like skull roofs, and beach reptiles that weren't paying attention. The roof bones show the familiar Pitton Ridge sculpturing and a crisp map of lateral line canals, so it is still hunted by feel in turbid water. Eyes sit high for periscope mode, and the nars ride forward enough to breathe while the skull stays hidden. But biomechanics flips the emphasis. Rather than relying mostly on suction, Cyclotosaurus likely used a short forward lunge and a hard clamp, then head twist to shear and subdue. The vaulted palate and reinforced cheek bars stop the skull from flexing under that twist, an amphibian answer to the crocodile's infamous death roll. Its world spanned much of Pangaea's monsoonal belt. In Central Europe's Cooper basins, Poland's lake beds, and India's Malari-type deposits, sediments record boom and bust hydrology, rising waters that open migration corridors, then long drawdowns that stranded fish in shrinking pockets. Cyclotosaurus profited on the boom, moving along freshened inlets where oxygen ran high and prey streamed in. During busts, it ruled the last deep holes, when lungfish and thick-scaled semionatids packed tight, and a single lunge could pay off big. Isotope signals in stereospondal phosphate point to freshwater residency. If Cyclotosaurus ever tasted brackish water, it was likely in low salinity deltas, not open estuaries. What did it eat? In related forms, the tooth microweir story says that the tips are smooth and there isn't much chipping. Soft tissues are caught, not shells broken. But the fact that the skull is stronger suggests that Cyclotosaurus often beat bigger, tougher food than flatheads did. Think of armoured fish, young etosaurs, or procolophonid lizards that were stuck in mud, or even smaller temnospondyls. Bite marks on bones from animals from the time show U-shaped cuts spaced out like stereospondal teeth. Some of the marks have healed, showing that not all ambushes ended neatly. Cyclotosaurus probably lived along current breaks and undercut banks in pools, where phytosaurs watched channels and Metoposaurus stacked the bottoms. Its heavier head and stronger clamp helped it do well there. Sensory and hearing matched Merck. Like its kin, Cyclotosaurus probably had weak airborne hearing but strong low-frequency sensitivity through the skull and lateral line. The pineal opening on the roof, common in temnospondyls, would have given it a light-sensing third eye to help time basking and depth choices as stratified waters warmed and cooled each day. The otic notch behind the skull roof, reduced compared with purely suction feeders, may reflect rearranged soft tissues linked to pressure equalization during hard jaw closures, rather than maximizing acoustic function. If Cyclotosaurus ruled the Triassic channels with clamp and twist power, step back to the Permian of Texas to see where that shoreline playbook began. Eryops, the river's edge enforcer, turning bars and eddies into kill zones. Eryops, early Permian Texas tank. In what is now north-central Texas, there is an early Permian river with heavy, wide footprints that run along the shore. The tracks go from the shallows up to sandbars and then disappear into reed beds. Those are from Eryops megacephalus, a big-bodied hunter that lived where land and water met. Eryops was about 1.5 to 2 metres long and had a skull that was about 0.5 metres across. It was built like a low bulldozer with a barrel chest, heavy limb girdles, and a bone-reinforced skull that was made to bite, hold, and not let go. Its head tells its structure what to do. The roof of the skull is made up of many thin skin plates with pits and ridges that are connected by natural sutures that lock them together. These sutures act like steel against twisting forces. It has a small, wide snout with labyrinthine teeth that are shaped like cones and fit together when the lips close. The vomids and pterygoids have tooth spots on the palate just inside the edges. These are called palatal fangs, and they make the mouth look like a clamp. You can hit a fish or a coastal reptiliomorph with your first bite, and it will pin it. The palatal posts will keep it from backing out, and the neck and trunk will shake and cut the rest of the way. The tips of the teeth on examples from Texas show polished wear with little chipping, which suggests that they ate soft-bodied food instead of breaking shells. Unlike the later pancake-flat lake-trap temnospondylus, Eryops kept its skull deep through the cheeks and its jaws tall, a geometry that favours leverage. The adductor chambers behind the eyes are broad and long, room for big jaw-closing muscles. The quadrate joint sits low and stout. When the mouth shuts, force travels straight into the reinforced palate rather than flexing the snout. Biomechanically, it's a grip and wrench head more than a suction plate, ideal for grappling struggling fish, xenocanth sharks, and mudbank tetrapods in moving water. Skull grooves show an ontogenetic story. Juveniles carry clear lateral line canals, a pressure-sensing system perfect for life as a gilled larva or small aquatic hunter in quiet backwaters. In adults, those canals are reduced or absent on many skulls, and the bone sculpturing coarsens, signals that older Eryops spent more time semi-terrestrial, using sight and vibration through the ground as much as hydrodynamic cues. The Starpes, ear bone, is stout and load-bearing, not the delicate rod of later hearing specialists. Airborne hearing was poor. Underwater and in mud, Eryops likely sensed low-frequency tremor through the skull and limbs. Limb sections show thick cortical bone with a relatively small marrow space, dense enough to aid buoyancy control near the bottom, but with remodeling and growth marks that indicate periods of faster, then slower growth as seasons shifted. In the Clear Fork and related red bed units, rivers rose in wet pulses and fell under long, dry spells. When levels dropped, fish and xenocanths packed the remaining channels. When storms hit, fresh, oxygenated water brought migratory prey upstream. Eryops's build, mobile on land, stable in current, let it work both ends of that cycle, bask and watch from a bar, slide into the eddy, strike, and haul back out to reposition. Amphibian reproduction continued. Eggs and early stages of larvae were attached to water. Hatchlings had lateral lines and external gills, but as they grew, they changed shape, giving up sense canals for stronger bones and limb shafts. Dragonfly nymphs, small fish, and safe cover were likely found in the shallow vegetation that juveniles hugged. Subadults then moved on to creek mouths and low-velocity bends before taking the main channel. Edops, the murkwater ambusher of the Permian swamps. In the late Carboniferous and early Permian, before crocodiles and other real reptiles took over the waterways, the swamps were watched over by something that looked like a cross between a frog and a tank. The Edops craigie was first found in the red beds of Texas more than 100 years ago. It was a frog with a broad skull that hunted in the murky shallows where it was hard to see and had to be patient. It was only about 2 meters, 6-7 feet long, so it wasn't the biggest hunter of its time. But its heavy skull, simple ear structure, and ability to sneak up on prey make it one of the most important examples of how frogs used to rule the edges of the earth. Edops belonged to one of the earliest temnospondyle families, bridging the gap between Carboniferous labyrinthodonts and the later, more specialized forms like Eryops and Mastodonsaurus. Its name literally means double face, a nod to its broad, blunt head, that took up nearly a third of its total body length. The skull alone could measure over 40 centimetres, 16 inches across. When you look at the bone, you see strength. Thick sutures interlocking like puzzle pieces, heavy ornamentation and a skull roof that looks almost hammered from iron. These features weren't for looks, they were for absorbing impact, resisting the torsional stress of fighting prey in confined, shallow water. Unlike the long-snouted fish-eaters that came later, Edops had a short, wide jawline packed with conical labyrinthodont teeth. Just behind the outer row sat its trademark palatal fangs, two large tooth-like projections anchored in the roof of the mouth. When the jaws snapped shut, these fangs locked with corresponding spaces in the lower jaw, forming a natural cage. Once anything wriggled inside, it wasn't getting out. The teeth show little wear or breakage, meaning Edops mostly took soft-bodied prey, fish, juvenile amphibians and aquatic insects rather than armoured reptiles. The environment of Edops was a transitional world, as coal swamps dried and new river systems carved across Pangaea's forming interior. The fossil beds of Texas and Oklahoma show floodplain deposits alternating with red clays, signs of seasonal flooding and evaporation. In wet seasons, rivers burst into shallow lakes teeming with fish and invertebrates. In dry seasons, these same basins shrank into warm, stagnant ponds. Edops was built for the in-between. Too heavy and slow to chase in open current, too aquatic to survive long droughts on land. Its survival strategy was simple: sit, wait, and strike. The skeleton reinforces the picture. The ribs are massive and slightly curved, enclosing a barrel-shaped body cavity that could store air, much like a primitive lung bellows. The limbs are stout and sprawled to the sides, with broad hands and feet adapted for pushing off soft mud rather than fast swimming. Its tail, thick but not especially long, acted as a rudder for short lunges. Instead of sleek pursuit, Edops relied on short-range bursts, like a frog's pounce in slow motion. Once it grabbed prey, its sheer mass and the friction of the mud helped anchor it in place as it shook its catch apart. Microscopic study of Edops bone tissue shows dense cortices and slow growth rates, implying a low metabolic lifestyle. It didn't need to move much, it needed only patience. In the still pools of the early Permian lowlands, that meant energy efficiency was survival. Its heavy skeleton also acted as ballast, keeping the animal neutrally buoyant just below the surface. This allowed it to hide beneath a thin veil of water, eyes and nostrils breaking the surface like small bubbles. Anything that swam within reach triggered the strike reflex, a forward snap of the jaw and a sudden pull of the limbs. Edops also shared its world with an evolving cast of rivals. In the same formations lived early reptiliomorphs like Simoria and amphibians such as Diplocaulus, along with freshwater sharks and lungfish. Unlike Eryops, which could haul out to bask or ambush at the shoreline, Edops seems to have preferred permanent water, avoiding overland travel except during floods. Its heavy body and weak limbs made it slow on land, but underwater it was nearly weightless, its low centre of gravity making it stable even in swirling silt. Archegosaurus, the river missile of the Permian. In Europe's Permian rivers, there was a long-nosed amphibian that moved like a torpedo and struck like a spring trap. This was a long time before alligators learned to hide and fish turned into giants. Archegosaurus decani, the river missile of the Saar Basin in Germany, was one of the most hydrodynamic early temnospondyls. Its skull shows that it learned to live almost entirely like a fish. At around 1 to 1.5 meters long, Archegosaurus looked at first glance like a small crocodile, an elongated body, 4 short limbs, a deep tail, and a narrow gharial-style snout lined with needle-fine teeth. But beneath the surface, it was still amphibian through and through, with smooth glandular skin, a labyrinthodont tooth pattern, and gills in its early life stages. Fossils from the Saar Basin preserve complete skeletons, even soft tissue impressions, showing a creature streamlined for fast pursuit in turbid, slow-moving rivers and floodplain channels that cut through the Permian lowlands of Central Europe. Archegosaurus's skull was a masterpiece of engineering for the sea. To cut through water with little drag, it was long, flat and narrow. Each jaw had a lot of small, evenly spread teeth that were great for grabbing fish that were moving around. The tongue had two sets of larger fangs that locked into grooves on the lower jaw, making a trap for soft food. This was similar to the Prionosuchus and Benthosuchus species that lived nearby. When it rushed, the mouth snapped shut and the teeth locked together like a zipper, making it impossible for fish to get free. Overall, the shape was great for quick, side-sweeping hits, like how gar and pike attack in bursts today. Running along the skull roof and down the body are shallow grooves, the lateral line canals, sensory systems inherited from fish. These canals housed neuromasts, vibration-sensing organs that let Archegosaurus detect pressure waves from swimming prey or rival predators. In dark, silt-laden water, eyesight alone wasn't enough. The lateral line made it possible to hunt in near blindness, turning every ripple into a location signal. Its large orbits also helped, giving it wide binocular coverage near the snout tip for tracking quick movements in the shallows. The neck and body of Archegosaurus tell a story of specialization. The vertebrae show reduced intercentra and long neural spines, creating stiffness along the trunk and flexibility in the tail, an ideal combination for tail-powered swimming. The ribs are short and light, minimizing resistance. Limbs are small and flattened, more like stabilizers than walking legs. When tucked against the body, they let the animal accelerate like a fish. The tail, on the other hand, is deep and laterally compressed, with evidence of tall fin rays near its end. In effect, Archegosaurus was one of the first amphibians to adopt a fish-like propulsion system, relying on tail beats for thrust rather than limb paddling. It spent all of its time in water. Bone histology shows that the structure is soft and light, which is typical of animals that live in water all the time instead of moving between land and water. Not thick, like the bones of some half-alien ambushes, like Eryops, the limb bones are porous. Because it was so light, Archegosaurus had great control over how much it sank. It could float in mid-water or cruise along mid-depths, saving energy while using its horizontal line to look for movement. It probably only came up for a short time to breathe, using its long, high-set lungs. Paleo-environmental data from the Saar Basin indicate a warm monsoonal climate with extensive wetlands and sinuous rivers that flooded seasonally. During high water, Archegosaurus would have dispersed through open channels, hunting in schools of fish. During low flow, it probably retreated to the deeper pools, lurking among submerged roots. Juveniles, discovered in abundance at the same sites, still show external branchial arches and gill traces, proving that they passed through a fully aquatic gilled larval stage before metamorphosis. Adults lost the gills, but retained the streamlined proportions of a fish hunter. Archegosaurus also carried a clue about the evolution of amphibian respiration. Inside its skull, the palate openings, choanae, show an intermediate arrangement between external and internal nostrils, suggesting early experimentation with airflow control between breathing and water feeding. It could surface quietly, take a gulp of air, and dive again without exposing much of its head. This adaptation foreshadowed later more efficient air breathers like Benthosuchus and Trematosaurus in the Triassic seas. Trimerorhachis, the salamander dragon of the early Permian. A strange animal moved slowly along the wet bottom of the early Permian floodplains in Texas and New Mexico. It looked like a living fossil. It had a flat head, a wide body, and gills that moved like red bands. It looked like a cross between a salamander and a dragon. This was Trimerorhachis insignis, a frog that lived in water and was so good at it that it never really left. Trimerorhachis lived its whole life in slow-moving pools and backwater channels. It ruled the quiet areas that bigger predators ignored because it had external lungs, thick bones, and long fins. At just over 1 metre long, Trimerorhachis wasn't a giant, but it was tough, widespread, and successful. Dozens of beautifully preserved fossils from Texas's Clear Fork and Archer City formations show individuals at different ages, larvae, juveniles, and adults, giving paleontologists an almost complete look at its biology. It belonged to the Dinosaurian temnospondyls, an early branch of amphibians that retained many ancestral fish-like traits. Its skeleton and lifestyle reveal how amphibians first experimented with staying underwater permanently instead of moving between land and water like Eryops or Edops. The head of Trimerorhachis was broad, flat and rounded, with a short snout and tiny eyes on top of the skull, an arrangement perfect for resting just under the surface. The jaws were packed with small, recurved teeth designed for catching insects, crustaceans and small fish. Inside, the palate bore smaller fangs arranged in patches, helping to grip prey before swallowing it whole. Unlike many of its Permian relatives with heavy, crushing skulls, Trimerorhachis had a lightly built cranium ideal for quick lunges in shallow water. Outside gills, feathery structures that grew from behind the skull and moved with the current, were what made it stand out the most. Several fossils of these gills have been kept with great clarity. They look a lot like the gills of current axolotls. They show that Trimerorhachis went through pedomorphosis, which means it kept features from being a young animal as an adult. Many frogs changed into forms that could breathe air, but Trimerorhachis stayed as a larva its whole life. That meant it never got big lungs or strong legs for walking. Instead, it learned how to live in the water perfectly. The body was long and low, with dense, compact bones that acted as ballast, keeping it anchored on the bottom instead of floating upward. Its ribs and vertebrae were heavy, while the limbs were short and flattened, more paddles than legs. The hands and feet had broad digits, possibly webbed for pushing against mud or slow sculling through still water. This combination of weight and paddle shape made it a bottom walker, creeping along the substrate like a salamander rather than swimming in open water like a fish. Fossil trackways and mass bone beds from the Clear Fork beds suggest that Trimerorhachis lived in crowded colonies, perhaps congregating during the dry season when rivers shrank into isolated pools. Some bone beds contain dozens of individuals layered together, their bones perfectly articulated, evidence of sudden burial by flood sediment or drought-induced die-offs when oxygen levels plummeted. The bones show minimal weathering or scavenging, implying the animals lived and died where they were found, rather than washing in from elsewhere. Even more is learned from the gills. The strands that have been kept in fossils have fine striations that look like blood vessels. This shows that they worked like real respiratory organs and weren't just pretty extras. Some fossils even show a row of ossified support rods, called branchial arches, that held the gills in place. There is very little clear fossil proof of soft tissue, but Trimerorhachis is one of the best known fossils of an adult amphibian that had gills that stayed in place. Its sensory adaptations also reveal a life spent in murk. Like other temnospondyls, Trimerorhachis had a lateral line system, a chain of sensory pores running across the skull and body that could detect pressure changes in water. With small eyes and poor hearing, it depended on this system to locate movement. That meant it didn't need clear water or daylight, perfect for the muddy, debris-filled channels of the Permian Plains. Despite its modest size, Trimerorhachis was a biological survivor. It lived through fluctuating climates and major ecological transitions, persisting long after many of its contemporaries vanished. Its success lay in not changing, in keeping a body plan that simply worked. the ability to remain aquatic, reproduce in water, and breathe through gills gave it a permanent refuge, even as the continents dried out around it. From the pedomorphic bottom walker that owned Permian backwaters, the scene jumps past Earth's greatest die-off to a sleeker heir of the currents, Benthosuchus, rising in the early Triassic to turn recovery rivers into hunting lanes. Benthosuchus, the river king after the Great Dying. Many species died out at the end of the Permian period and the beginning of the Triassic. For a while, the world's waters were still. Then new life came back, and a master of the water came with it. Benthosuchus sushkini, whose name means creature of the deep, first showed up in what is now Russia as one of the first big predators to do well after the disaster. It was Archegosaurus's child, a relative with the same long body shape for hunting fish, but changed it to fit the unstable, oxygen-poor rivers of a new Earth. Benthosuchus lived around 250 million years ago during the early Triassic, when global ecosystems were still rebuilding. The Siberian floodplains where it swam were filled with silty rivers, murky lakes, and estuarine channels. These waters carried the debris of a recovering planet, and they also carried the perfect conditions for a stealth hunter. Fossils found in the Wetluga River basin near the village of Bentha, which gave the animal its name, show that it was about 2 meters long, sleek and streamlined, with a head built for speed and precision. The skull of Benthosuchus was long and crocodile-like, narrow at the snout and widening toward the back. Its jaws were lined with fine, sharp teeth that locked together like interdigitating blades, perfect for gripping fish rather than crushing them. Just like its Permian ancestors, the palate carried a second set of inward-facing fangs to pin slippery prey. Its orbits faced upward, giving it binocular vision, while the rest of its body stayed hidden below. The head's upper surface was etched with grooves of the lateral line system, an underwater sensory network that picked up even the faintest ripples. It could lie buried in silt and still feel a fish's movement before seeing it. Unlike the broad, flat ambushes of the Permian, Benthosuchus had a more streamlined skeleton. The vertebrae are tightly connected and slightly taller, stiffening the body for fast, side-to-side swimming. The ribs are shorter, reducing drag, while the tail vertebrae show a strong keel, evidence of a powerful, laterally compressed tail fin. The limbs were still small, used for steering rather than walking, and the shoulder and pelvic girdles were light. Everything about this animal says mobility. It wasn't a rock on the bottom like Trimerorhachis. It was a torpedo that could surge through water in short, controlled bursts. Its skull shows clues to one of the most important evolutionary experiments of its time: partial air breathing. The nostrils were positioned farther back on the snout, and the internal passages, choanae, opened wide, showing that Benthosuchus could take quick gulps of air from the surface. The roof of the mouth was vaulted and rigid, a structure that might have helped separate breathing and feeding. In a world where rivers often went stagnant, that mattered. Early Triassic waters were low in oxygen, so the ability to supplement gill respiration with occasional lung breathing was a survival edge. Fossil deposits from the Wetluga region paint the setting vividly. The Wetluga series contains alternating layers of claystone and sandstone, a record of seasonal floods and quiet pool phases. Between these layers, paleontologists have found entire bone assemblages of Benthosuchus, fish, and early amphibians. Some specimens were preserved and curled, suggesting sudden burial after flood events. This points to a predator that prowled shallow channels and oxbow lakes, hunting smaller amphibians, lungfish, and bony fishes that dominated early Triassic waters. The size and shape of its skull place it near the base of the stereospondyle lineage, a group that would later produce river monsters like Mastodonsaurus and Cyclotosaurus. Benthosuchus was smaller and lighter than those later giants, but it set the pattern. A head designed for ambush, a tail for propulsion, and a body tuned for quick acceleration. In life, it likely floated mid-depth, using gentle tail movements to maintain position. When prey came close, it lunged forward, opened its jaws in a rapid suction motion, and drew its meal into the trap. Some scientists believe Benthosuchus may have been one of the first amphibians to re-enter slightly salty water. Fossils found in sediments that once bordered ancient estuaries suggest limited salt tolerance, possibly an early step toward the later Trematosaurids that fully colonized coastal environments. Its smooth, thin skin and physiological flexibility would have helped it withstand brief exposures to changing salinity, a valuable adaptation in unstable climates. Wetlugasaurus, the Arctic stream hunter. Rivers and lakes slowly came back to life after the biggest mass extinction the world had ever seen. This happened even in places where it was cold and dark for half the year. Wetlugasaurus was a frog that lived in the early Triassic Arctic drainages in northern Russia. It built an unlikely kingdom. It was one of the first big cats to live in the cold, fast-moving streams of what would become Siberia. With its big eyes, strong tail and broad head, this animal showed that frogs could not only live on Earth after the end of the world, but also take over the very edge of it. Wetlugasaurus lived around 250 million years ago, and its fossils are among the oldest found in Arctic Russia's Wetluga and Vychegda river basins. Measuring about 1.5 to 2 meters long, it wasn't a true giant, but its proportions were formidable. A flat skull nearly half a meter across, a strong muscular tail, and paddle-like limbs built for maneuvering through fast water. Like its close relative Benthosuchus, it was a stereospondal temnospondal, part of the great radiation of amphibians that dominated freshwater ecosystems during the early Triassic recovery. But Wetlugasaurus went further north and adapted to colder, more turbulent water than any amphibian before it. The form of its skull was the most noteworthy aspect about Wetlugasaurus. Its wide, triangular head had big pupils, and its huge eyes suggest that it hunted visually, maybe even when it wasn't light outside. In the Arctic, where it doesn't get light for long periods of time, having big eyes was clearly a plus. The bones on top of the skull are thick and have deep grooves carved into them. The lateral line tubes are also very well developed. These are sensory adaptations that help the animal feel vibrations and changes in water pressure. When it got dark and muddy in streams, those tunnels turned the whole skull into a motion detector. The jawline of Wetlugasaurus was powerful but flexible. The teeth were sharp and curved, arranged in tight rows along the jaws and palate. Unlike Eryops, which relied on brute force, Wetlugasaurus combined speed and suction. When it struck, it opened its mouth rapidly, creating negative pressure that pulled prey in before the jaws snapped shut. Inside the palate, rows of smaller teeth prevented escape. Its targets were fish, crustaceans, and smaller amphibians, anything that could fit down its throat. Fossil evidence shows that Wetlugasaurus lived in river systems fed by glacial meltwater and seasonal floods. The sediments where it's found are coarse and layered, suggesting swift currents alternating with calm depositional periods. That environment demanded both power and control, and Wetlugasaurus had both. Its tail vertebrae were long and tightly linked, forming a deep, fin-like structure for propulsion. The ribs were short and sturdy, giving the body a compact, hydrodynamic shape. The limbs were relatively small, but the shoulder and pelvic girdles were strong, indicating they helped steer and brake. It could burst forward to strike, then use its limbs to stabilize and pivot in the flow, behavior similar to modern river otters or crocodiles. Its bone structure provides key insights into its lifestyle. Thin section analysis reveals lightweight, spongy bone, evidence of near-neutral buoyancy, meaning it could hover mid-water without effort. This was critical in icy rivers, where conserving energy meant survival. Compared with denser-boned, bottom-walking species like Trimerorhachis, Wetlugasaurus was a free-swimming hunter, able to glide through water columns and follow prey schools as they moved with the seasons. The Arctic Triassic world was unlike today's frozen tundra. It was warmer, though still marked by long seasonal extremes, months of light followed by months of twilight. Wetlugasaurus likely timed its feeding and breeding cycles to this rhythm. In summer, as meltwater floods expanded the rivers, it would disperse across wide floodplains. In winter, it probably retreated to deeper channels that stayed unfrozen beneath the ice, lying sluggish in near stasis. Its metabolism slowed almost to a standstill. The ability to endure cold, oxygen-poor water was likely one of its greatest advantages. The remains of Wetlugasaurus are also captivating because they show the beginning of a new stage in the development of amphibians, the change from living only in fresh water to living in brackish and coastal environments. Some of them are found in layers of dirt that formed near delta plains, which are places where rivers met small seas in the past. Chemical signs in their bones show that they could handle mild saltiness. This could have been because they hunted in waterways when there wasn't much game in the land. This means that Wetlugasaurus was one of the first frogs to test the coast. The salt-tolerant Trematosaurus and its descendants later made this route even better. Trematosaurus, the amphibian that invaded the sea. Early Triassic was a rough time for the world, and most frogs stayed near rivers and swamps. But one brave species went in a different direction. It went beyond fresh water and into bays along the coast, where salt water, waves, and land met. This leader was Trematosaurus brownie, which was one of the first frogs to live in and maybe even thrive in marine settings. Trematosaurus was the first amphibian to explore the ocean. Its long streamlined body, salt-ready physiology and pointed head made it a genetic experiment that crossed the river and the sea. Trematosaurus lived around 247 million years ago, not long after the Permian extinction wiped out most life on Earth. Its fossils have been found across Europe, Madagascar, and South Africa, proving it spread widely across Pangaea's coastal lowlands. Reaching up to 2.5 meters in length, it wasn't enormous, but its body was a blend of elegance and power. It was part of a new amphibian order, the Trematosaurids, descendants of Benthosuchus-like ancestors that had refined the art of swimming and begun to exploit the brackish edges of the ancient world. The skeleton supports this life in water. The limbs are short and the legs are light. The tail is long and squeezed on the sides, making it a strong organ for moving. The fact that its arm and hip girdles were small shows that it spent most of its time in water. The neural spines on the vertebrae are well developed, which makes the body stiff so that the tail can beat quickly. It could stay in a straight line even in fast current and speed up for short periods of time, which was important for chasing prey in open water or along tide channels. The most amazing thing about Trematosaurus, though, was that it could live in salty places. Marine creatures and coastal sands are fossilized with its bones, which shows it hunted where rivers meet the sea. The nearby rock's chemical makeup shows evaporate crystals like halite and gypsum, which show that the saltiness has been changing. Most frogs would have died in those conditions, but Trematosaurus had learnt to deal with some of them. Modern frogs lose a lot of water when they are in salty settings, but Trematosaurus' thick glandular skin, which was thicker than that of its freshwater cousins, probably kept it from drying out. Its kidneys may have been better at getting rid of salts, which is an important step toward real sea life. Its habitat was dynamic: estuaries, deltas, and coastal lagoons filled with shifting sandbars, mangroves, and tidal creeks. These were rich ecosystems, teeming with early fishes, ammonites, and small reptiles. Trematosaurus hunted by stealth and speed. Using its large eyes and lateral-lined system, it could sense the vibrations of prey swimming above. Then, in one quick motion, it launched upward, jaws snapping like shears. Its long snout made it ideal for precision strikes, similar to modern gharials or needlefish. Once prey was caught, a sharp sideways flick of the head stunned or killed it, before swallowing. The climate of the early Triassic suited this amphibian explorer. After the chaos of the Permian extinction, Earth's temperatures were rising again, and vast shallow seas covered continental edges. Monsoon patterns washed nutrients from land into the oceans, creating fertile estuaries. Trematosaurus filled the top predator role in these zones, preying on fish and early marine reptiles that hadn't yet diversified. It was agile, opportunistic, and likely territorial. Fossil assemblages show individuals of varying ages, suggesting that juveniles occupied protected bays while adults hunted farther offshore. Fossil bone histology reveals an amphibian in transition. Its bones are less dense than those of its river-bound ancestors, reducing weight for more efficient swimming. The limb bones show less muscle attachment, consistent with reduced walking ability. Yet despite its aquatic commitment, it still needed to breed in fresh water. Eggs and larvae couldn't tolerate salt water, so Trematosaurus likely migrated upriver during breeding seasons, just as modern amphibians and fish do. Once the young matured, they drifted downstream to coastal feeding grounds, a life cycle that blended river and sea in one of nature's earliest migratory patterns. Gerrothorax, the living bear trap of the Triassic. The most astounding thing about Trematosaurus, though, was that it could live in salty places. Marine creatures and coastal sands are fossilized with its bones, which shows it hunted where rivers meet the sea. The nearby rock's chemical makeup shows evaporate crystals like halite and gypsum, which show that the saltiness has been changing. Most frogs would have died in those conditions, but Trematosaurus had learned to deal with some of them. Modern frogs lose a lot of water when they are in salty settings, but Trematosaurus' thick glandular skin, which was thicker than that of its freshwater cousins, probably kept it from drying out. Its kidneys may have been better at getting rid of salts, which is an important step toward real sea life. Gerrothorax belonged to a group of amphibians called Plagiosaurids, a lineage that took the ambush lifestyle to its logical extreme. It was about 1 meter long, squat and broad, with a head nearly as wide as its body. Its skull was flat as a dinner plate, with small, widely spaced eyes sitting high on top like twin periscopes. It spent its life lying on the riverbed, buried in silt or vegetation, watching upward. And when something swam overhead, a fish, a small reptile, or even another amphibian, it didn't rise or lunge. It simply opened its jaws like a trapdoor, creating a sudden vacuum that sucked the victim straight in. That feeding style was its signature. Most predators move their lower jaw to bite. Gerrothorax moves the upper jaw instead. Its lower jaw stayed anchored, hinged to a rigid, immobile base. The top of the skull lifted upward using a strong set of neck muscles, turning the entire head into a suction pump. Water and prey were pulled in within milliseconds. This bizarre mechanism, confirmed by 3D digital reconstructions of its fossils, shows that it used suction feeding more efficiently than almost any other amphibian of its time. The skull's roof bones were heavily reinforced to withstand the pressure of repeated rapid openings and closings, while the internal bones of the mouth formed a funnel-shaped cavity to maximize water flow. Its teeth made it even more dangerous. They were short, cone-shaped and bent backwards, making them great for holding onto instead of cutting. It had rows of extra teeth on the roof of its mouth. These were the palatal fangs that temnospondyls are known for. Once its food was in its mouth, it couldn't get away. Its design was all about control and efficiency. It had a wide head for suction, a short neck for leverage, and a rigid skeleton to take the shock of water coming in. It didn't chase. It ate its food while it was still living. The rest of its body matched its predatory patience. The limbs were short and wide, with strong joints capable of anchoring it into muddy bottoms. The tail, unlike the deep, finned tails of swimming amphibians like Benthosuchus, was low and broad, built more for balance than propulsion. Bone histology studies show that Gerrothorax had very dense bones, giving it natural ballast. It could sink and stay flat on the bottom without effort. This allowed it to rest for long periods, motionless, conserving energy in oxygen-poor water, where most other predators would suffocate. It lived in a harsh climate, with small floodplain lakes that dried up and filled back up with water, plants growing along the edges and algae covering the surface. In northern Pangaea, the late Triassic was warm, had seasons, and was prone to droughts. As the water level dropped, ponds became still, and oxygen levels dropped sharply. That was death for most of life. The time for dinner for Gerrothorax had come. Smaller amphibians and fish that were in the same group slowed down or floated near the top, making them easy food for something that never had to move. When it rained again and the channels filled with water again, Gerrothorax would spread again, taking over any low oxygen areas that other animals avoided. Platyhystrix, the sail-backed amphibian of the Permian. In the Carboniferous swamps and Permian plains of what is now the southwestern United States, there was a strange frog with a dramatic sail along its back. This was long before dinosaurs and even before lizards became powerful. It was called Platyhystrix rugosus and looked like a mix between a salamander and a small dimetrodon. It looked like no other animal on Earth because its tall, hard spines rose from its backbone like the ribs of a fan. This animal was rarely more than 1 metre long, but its fossils are so interesting that paleontologists are still not sure what its sail was for: to show off, to keep the temperature down, or to protect itself. Platyhystrix was a close relative of Dinosaurs and other early temnospondyle amphibians, yet it broke the mould. While most of its kin were heavy, flat-bodied ambushers that lived in ponds and marshes, Platyhystrix spent much of its time on land. Its bones show strong limb girdles, compact vertebrae, and thick skull bones, features that supported a semi-terrestrial life. The most recognizable feature, however, is its neural spine sail, formed from elongated vertebral spines, sometimes more than half the body height. These spines were laterally flattened and textured with deep grooves where skin and blood vessels once attached. Along each, a web of soft tissue once stretched, creating a sail that could have been vividly coloured in life. The function of that sail remains one of the most discussed puzzles of early amphibian paleobiology. Early researchers thought it might have been used for thermoregulation, acting like a solar panel to warm the blood during cool mornings, or radiate excess heat in midday sun. The theory fits with the dry, variable climate of the early Permian, where daily temperatures could swing sharply. A blood-rich sail could have let Platyhystrix start its day faster than its competitors. Later studies, though, proposed a different role: species recognition or sexual display. No two individual sails seem identical. Some were tall and narrow, others shorter and broader. The pattern might have helped mates or rivals identify one another across the floodplains. Either way, the sail was not just for show. It was alive with blood vessels and nerves, and any wound would have been painful and dangerous, meaning predators learned quickly not to bite there. Its body structure shows that it used the land even more. The ribs were tightly bound together, making the body strong enough to hold weight when it wasn't underwater. The arms were short but strong, and the hands and feet were broad and flat, with claw-like tips for gripping soft mud. Platyhystrix was different from most early frogs because it had dermal armour plates, which were bony scutes lodged in its skin on its back and shoulders. These helped the sail base stay in place and gave it extra defence against early land predators like Dimetrodon and Ophiachodon. With its armour, sail and squat shape, Platyhystrix was no weak frog. It was like a tank made for the rough edges of old lakes. Fossil beds in Texas and New Mexico's red sandstones show the world it lived in. Braided rivers, seasonal pools, and sparse fern scrubs stretching beneath a harsh Permian sun. Platyhystrix shared this environment with small reptiliomorphs, amphibians such as Eryops, and primitive synapsids, the early relatives of mammals. In these habitats, water levels rose and fell constantly. Amphibians that could haul themselves across land between ponds held the advantage. Bone histology shows a dense outer cortex and medullary cavities filled with spongy bone, a compromise between buoyancy in water and strength on land. This suggests it spent part of each day basking on exposed mudbanks, warming under the sun, while smaller amphibians remained hidden. Platyhystrix likely preyed on insects, arthropods, and tiny vertebrates, snapping at anything that moved within reach. The broad skull and quick bite gave it precision, while its armour protected it from counterattacks. Some paleontologists think the sail might have helped it appear larger to predators, puffing up its outline when threatened. In combination with its raised posture and harsh croaks, if its throat structure resembled modern amphibians, it could have looked and sounded far more intimidating than its modest size suggested. From a sun-warmed sailback prowler stalking mudbanks, the camera sinks into the Karoo's dark waterways, where Rhinesuchus trades display for stealth and turn still, tea-coloured pools into silent kill zones. Rhinesuchus, the swamp hunter of the late Permian. This animal ruled the rivers of old South Africa long before crocodiles did. Rhinesuchus was the most dangerous animal in the late Permian swamps. It had a low, broad skull, huge jaws, and a body designed to hide. Its remains, which can be found in the red mudstones of the Karoo Basin, describe a world that was almost dead. It was a humid land that was slowly drying out, and the last great frogs were fighting to stay alive as reptiles took over. Rhinesuchus, meaning nose crocodile, was a stereospondal temnospondal, one of the largest amphibians of its time, stretching nearly 3 meters, 10 feet long. Its skull alone could exceed half a meter, with a wide triangular shape and a snout armed with conical teeth. From above, it looked like a crocodile, but its lineage was far older. The top of its skull was thick and heavily ornamented with ridges and grooves, while the eyes sat high on the head, perfect for watching prey from just beneath the surface. Its nostrils were also placed near the top, allowing it to breathe while remaining hidden. The jaw structure of Rhinesuchus reveals how it fed. Its teeth were sharply pointed, arranged in a single outer row, and additional palatal fangs inside the mouth. These teeth didn't cut, they gripped. When the jaws snapped shut, anything between them, a fish, small reptile, or amphibian, was held tight by interlocking spikes. The skull roof and cheekbones were tightly fused, creating a rigid platform that could handle powerful bites. However, the neck vertebrae were relatively weak, meaning Rhinesuchus didn't twist or thrash its prey the way crocodiles do. Instead, it likely used suction and leverage, pulling food under and holding it until it stopped struggling before swallowing it whole. The body of Rhinesuchus was heavy and flat, built for stability in shallow water. Its ribs were broad and its tail was thick, laterally compressed and muscular, an excellent propeller for sudden bursts. The limbs were short and strong, allowing it to push off the muddy bottom or drag itself onto land to bask. Bone density studies show it had compact, weighty bones, giving it neutral buoyancy near the riverbed. Like a living log, it could float nearly motionless, using minimal energy while waiting for something to wander too close. The Karoo Basin was a rich, complicated wetland system in the late Permian. It had rivers, ponds, lakes, and conifer trees and ferns all around it. Rhinesuchus lived with early fish, lizards, and smaller frogs. There were fast changes going on though. Wetlands were drying up because of changes in the climate, and regular droughts were getting worse. For an animal that needed water so much, change was very important. Rhinesuchus could survive for a short time on land, probably resting in wet caves or shady mudbanks when the water level was low, but it never went very far from the water. Amazing sensory changes can be seen in the anatomy of the skull. Its lateral line tubes are shown by grooves on the surface, which are used to pick up on ripples and movement in the water. The pressure-sensitive cells in these tubes could feel a fish's fin flick or a reptile's wave as it swam. The Rhinesuchus was a deadly hunter in murky, oxygen-poor ponds thanks to its lateral line system. Because its eyes were facing upward, it could watch the surface without moving, which made it perfect for sneaking up on its prey. When it saw its food coming, it would jump up with its tail and strike with its wide open teeth. Paracyclotosaurus, the armoured colossus of the Triassic rivers. There were a lot of species that died out at the end of the Permian, but then there were lots of predators in the rivers again. He was one of them. It was so big and strong that even early snakes stayed away from it. The name of this huge animal was Paracyclotosaurus davidi, and it lived in India, Australia, and some parts of Africa in the middle to late Triassic period. It had a skull as wide as a door and jaws strong enough to break bone. It was one of the biggest frogs that had ever lived in fresh water. It was a relic from a time when amphibians could still compete with snakes. Paracyclotosaurus reached nearly 3 meters, 10 feet in length, though its skull alone could exceed half a meter. It belonged to the stereospondyle family, the same lineage as Mastodonsaurus and Cyclotosaurus, but took the robust design of those predators even further. Where Mastodonsaurus had a flat, shovel-like head, Paracyclotosaurus' skull was deeper, heavier, and heavily reinforced, almost architectural in structure. The roof bones interlocked tightly, and its palate was vaulted like an arch, distributing the immense pressure generated during a bite. Every surface of the skull was textured with pits and ridges, evidence of thick, vascularized skin, the same feature that helped modern crocodiles sense pressure changes in water. Paracyclotosaurus's molars were full of cylindrical teeth that were designed to pierce and hold rather than slice. There were several sets of huge palate fangs behind the outer row of teeth. Together, they formed a cross-shaped trap for food. It had low and wide-jawed joints that let it close with a long circle. This is what gave it its killing power. It had huge adductor chambers, which are where jaw muscles connect. They were as big as those in animals that are much bigger. When its lips were closed, the force of its bite was probably about the same as a current crocodile of the same size. Bite marks on Triassic fish bones and small reptile skulls found in the same layers match exactly with the spacing between Paracyclosaurus teeth, proving that it was a top-level hunter that hid in wait. The body that supported that skull was no less impressive. Fossils from India's Panshay Formation and Australia's Nimboida beds reveal a stocky, barrel-chested torso with short, powerful limbs and a deep tail. The bones of the pectoral and pelvic girdles were dense and broad, forming platforms for muscle attachment. Paracyclotosaurus wasn't a fast swimmer like Wetlugasaurus. It was a power lunger, an amphibian tank designed to sit motionless on the riverbed and explode upward when prey passed overhead. Its tail was muscular and slightly flattened, providing quick bursts rather than sustained speed. Microscopic bone structure supports this picture. Its limb bones show dense, compact tissue with little internal sponginess, meaning it was heavy-bodied and neutrally buoyant, able to stay anchored to the bottom without floating up. Combined with its low-slung skull and sensory canals, this weight allowed it to remain perfectly still for long periods, conserving energy in slow-moving waters where oxygen was scarce. When prey approached, it didn't chase. It ambushed, jaws opening with explosive power and closing before the victim even realized the danger. It lived in a world that was still changing after a disaster. Continental drift had started to separate Pangaea into areas that were dry and areas that were wetter. This made huge floodplains where the water level changed all the time. Strong skeleton frogs with flexible lungs did well in this uncertain climate. Following the movements of its food, Paracyclotosaurus probably spent time in deep ditches when it was dry and in flooded areas when it rained. Bone isotope research shows that it could survive for a short time in salty water, possibly going into coastal lagoons like its relative Trematosaurus. Its diet was varied, but always carnivorous. Fossil evidence indicates that Paracyclotosaurus fed on large fish, smaller amphibians, and even reptiles that ventured too close to the water's edge. A unique set of ridges along its palate may have helped channel struggling prey toward the throat. Some scientists believe it could generate partial suction when opening its jaws underwater, though less efficiently than Gerrothorax. Once prey was secured, the head's reinforced design prevented flexing or bending, a crucial adaptation for handling heavy, armoured victims. Platyops, the river ambusher of the Permian floodplains. Under the weeds in the Permian marshes of what is now Russia, there was a shadow. It had a smooth, long, narrow body and a tail that moved just enough to stir up the mud, moving after that. When a fish got too close, their jaws slammed shut with a sound like wood being split. That was Platyoposaurus stuckenbergi, which was one of the best frog hunters of its time. It was sleek, sneaky, and perfectly suited to life in the river. In a world where the line between fish and amphibians was still fuzzy, it was a master at sneaking up on its prey. Platyoposaurus lived about 265 million years ago in the Middle Permian when the great supercontinent Pangaea stretched from pole to pole. The region that is now Russia was covered by vast river systems and floodplain lakes, warm and rich with life. Fossils of Platyoposaurus, including remarkably complete skulls, come from the Oka and Bela Bay formations near the Ural Mountains. They reveal a predator about 2.5 meters long, built low and lean with a long crocodile-like head, a powerful tail, and short sturdy limbs for anchoring in currents. What makes Platyoposaurus unique is the shape of its head. It was long, flat and triangular, and the curved teeth on the inside interlocked with each other to grip food instead of cutting it. The lips fit together like a puzzle, with each tooth touching the one next to it. There were more palatal fangs on the roof of the mouth, making a double set of traps that held food in place. The Platyoposaurus used strength and accuracy, while blunt-jawed frogs depended on suction. When it hit, the jaws didn't just snap shut, they clamped down, making sure that whatever went in would not come out living. Platyoposaurus had eyes that were high on the skull and pointed slightly upward. This made it perfect for hiding near the bottom of the water and watching what was going on above it. Paleontologists have found tiny traces of lateral line canals around the skull. This is the sensory system that frogs got from fish. The animal had an unseen map of its surroundings, thanks to these tubes that picked up on vibrations and water pressure. This made Platyoposaurus a live sonar machine in rivers that were too muddy and full of silt for it to see. Every flick of the fin or step on the bank of the river was like a pulse that it could follow back to its source. Behind that armed head is a body that was made to be stealthy and move quickly and explosively. The ribs were close together and thin, and the tail was long and strong with a small fin ridge. This made the body very smooth, which was great for rapid bursts of speed. Its bones were not too thick, so it could float just above the water without floating up. The legs were short, strong and webbed. They were not used for swimming, but for turning and balancing. It could stay put in moving water for hours at a time, barely moving until the right time to strike. There were slow-moving rivers, deltas and small lakes with lots of plants all around Platyoposaurus's home. It rained every rainy season, which made the waterways full. During dry seasons, they shrunk down to muddy ponds. It's possible that Platyoposaurus hid in soft mud during droughts to stay cool, going into a state of torpor similar to how lungfish and frogs do today. It could breathe through both air and water because its skin and lungs were smooth and porous. This gave it the ability to adapt to changing oxygen levels. Because it could change, it was one of the amphibian groups that lived the longest. In its ecosystem, Platyoposaurus had few equals. Large predators like the early synapsid Dimetrodon dominated land, but in the water, Platyoposaurus reigned. Its speed and precision made it the top aquatic hunter of the Permian floodplains. Smaller amphibians and reptiles gave it a wide berth, and even other stereospondylus rarely shared its niche. It was the amphibian equivalent of a modern crocodile, perfectly adapted to a world of murky rivers and seasonal floods. From the hidden hunter that ruled Russia's muddy floodplains, the timeline flows backward to an even stranger swimmer, Diplocaulus, the boomerang-headed amphibian whose skull turned water itself into a set of invisible wings. Diplocaulus, the boomerang-headed glider of Permian streams. Diplocaulus was the strangest animal that lived before the dinosaurs. It looked almost silly, with its wide boomerang-shaped head and thin salamander-like body. But its design was based on careful engineering. The curved wings on its skull weren't just for looks, they were a hydrodynamic tool that helped this animal steer, stay stable, and maybe even glide through old streams like a live kite. Over 20 million years ago, Diplocaulus ruled the calm rivers and ponds of North America and North Africa. It did well while bigger frogs fought for power. Diplocaulus, meaning double stalk, lived during the late Carboniferous to early Permian about 270 million years ago. It reached lengths of around 1 metre, 3 feet, modest compared to the giant temnospondyls of its time, but its anatomy was far more specialised. The most striking feature, the boomerang head, was formed by long extensions of the rear skull bones called tabular horns, sweeping outward like airplane wings. These lateral projections gave the head a span wider than the body itself, creating a flat, triangular shape unlike any other amphibian before or since. At first, paleontologists puzzled over this bizarre skull. Some thought it served as armour. Others believed it made Diplocaulus hard to swallow. But biomechanical and fluid dynamic studies later revealed the truth. The horns likely created lift as water flowed over them. In motion, they acted like hydrofoils, generating upward force that countered sinking and stabilized the animal's position in the current. That meant Diplocaulus didn't need to swim constantly to stay level. It could simply glide with minimal energy. The head also prevented rolling, much like a plane's wings prevent tipping. This adaptation gave Diplocaulus near perfect control in shallow, flowing water. High on the skull, its eyes were looking slightly upward. This gave it a wide field of view while it stayed hidden under the water. The nostrils were put close to the end of the nose so that it could breathe quietly while staying underwater. Their mouths were lined with rows of small, sharp teeth that helped them catch small animals like insects, crabs, and young fish. The Diplocaulus wasn't a strong hunter. It was a precise eater that moved quickly instead of lunging. Its small teeth suggest that it swallowed its food whole, using the force that was made when its mouth quickly grew bigger. Fossil evidence places Diplocaulus in floodplain ponds and slow-moving rivers across what is now Texas, Oklahoma, and Morocco. The rock layers preserving its bones often contain ripple marks, plant debris, and freshwater fish remains, signs of calm, oxygen-rich water. These environments teemed with invertebrates and small fish, perfect hunting grounds for a mid-sized amphibian. Unlike the giant temnospondyls that dominated deeper channels, Diplocaulus preferred the edges, shallow streams shaded by vegetation, where its coloration and shape provided camouflage from above. Its strange skull form may have also been used for defense. Predators had a hard time swallowing because the head was so big. Fossilized fish and frogs from the same areas show that some species were big enough to try to eat other animals, like Eryops and early sharks. Because Diplocaulus's skull had wings, Anyone trying to eat it would have had a hard time getting that huge head through its teeth. There are bite marks on the horns of some fossils which suggest that this plan worked more than once. Crassigorinus, the shadow of the Carboniferous swamps. Before crocodiles and other big sea reptiles, there was a sleek black animal that hunted in the deepest parts of Earth's woods. Its teeth were like traps, its arms were weak, and its body moved through the darkness like an eel. This was Crassigorinus scoticus, the thick tadpole. It was a very strange frog predator that scientists once thought it was a fish. It was the worst thing that could have happened in the Carboniferous swamps. It was a relic from a time when animals were still learning how to walk on land, and some, like Crassigorinus, chose to stay in the dark. Crassigorinus lived about 330 million years ago in what is now Scotland and North America. Its fossils come from the oil shales of West Lothian, ancient deposits formed in stagnant lagoons and floodplain lakes surrounded by towering club mosses and ferns. These were the cradle of amphibian evolution, the first humid jungles, where giant dragonflies buzzed overhead and millipedes longer than humans crept across the forest floor. But Crassigorinus stayed out of the sunlight. It ruled the dark, oxygen-poor waters beneath the roots, a top predator in a world that had only just begun to crawl. At around 2 meters, 6.5 feet long, it was built for stealth. Its body was long and sinuous, with a flexible spine and short, paddle-like tail. Unlike many of its terrestrial cousins, it had tiny, almost vestigial limbs, little more than stubs, with a few bones inside. This proved it was fully aquatic, unable to support itself on land. Its ribs were thin, the skeleton lightly built, and the skull streamlined. This combination made Crassigorinus a superb swimmer, undulating its body like a modern eel or Saecilian. Its movements were silent and effortless, perfect for stalking through weedy shallows or darting between submerged roots. The scariest thing about Crassigorinus was the structure of his head. The shape of it made it look more like a reptile than a frog. The jaws were long and had rows of sharp, conical teeth, some of which were over a centimetre long. These teeth were meant to cut and hold slippery food. Huge adductor muscles behind the eyes made the bite possible, giving it a vice-like grip. Inside the mouth, the tongue had more rows of teeth that formed a second set of spikes that held food in place after it was bitten. Everything was trapped when it shut its jaws, and nothing could get away. Fossil studies show that its skull could open very wide, which would have let it swallow whole big fish or even smaller amphibians. Its sensory systems were equally tuned for darkness. The skull roof is lined with deep grooves that mark the course of lateral line canals, pressure-sensitive organs inherited from its fish ancestors. These canals let it see through vibration, detecting the movements of prey long before sight could. Combined with its large eyes, Crassigorinus could hunt in complete murk, guided by ripples alone. In this way, it resembled both a catfish and a crocodile, but it was older than both, a pioneer of underwater stealth. Even though they are long gone, the giants of the amphibian age can still be heard in the croaks and stares of frogs and salamanders. They remind us of a time when they ruled both land and water. Every fossil we find is a reminder of a world that no longer exists. They show that monsters lived on Earth before the dinosaurs. Leave a like, subscribe for more trips into the past, and let us know what frog you'd fear or dare to meet in the primordial swamps if you were one of these animals.